Hello and welcome back to the Hutchins School Chemistry Lab. I'm Dr. James and today we'll be discussing synthesizing alcohols. Let's get to it. Our course document describes the following dot points, which I'm not going to read to you because you can pause and read them if you would like to. Suffice to say, this presentation is going to cover each of these points. We haven't talked much about alkynes before, but alkynes undergo reactions similar to alkenes. The only thing is the product of the reaction of some of those alkynes are indeed alkenes, and so they are able to undergo a second reaction just as the alkene would have originally been able to. Let's have a look at an example. Here we have ethyne, to which we can add hydrogen gas to produce ethene. If we add a second equivalent of hydrogen gas to this molecule, we can produce ethane. Now we could skip one of these steps by adding in excess hydrogen at the beginning, and from ethyne producing ethane. These presentations are going to talk to you about alkenes rather than alkynes. The assumption that if you have an alkyne present, you'll treat it in the same way as an alkene, but also be looking for a second reaction of that product alkene to form a saturated molecule as the final product. We've talked before about asymmetric small molecules in our review of physical sciences work, but we need to make sure that we're completely on top of the concept. You can add small molecules such as HX and H2O in addition reactions to unsaturated molecules, and multiple products may result. There's no guarantee there'll be multiple products, but it's a distinct possibility. In this example, we're going to add a hydrogen halide. This could be any of the halides, fluoride, chloride, bromide, or iodide, to an alkene. I'll give you a chance to name both of these molecules. Our reactant is but-1-ene and our product is 1-halobutane. You may have already deduced that a second product may indeed be formed in this particular reaction. Our second product in this case is 2-halobutane, and this occurs because we can add our halogen to either the 1 carbon or the 2 carbon of our reactant. For our course, they are treated as equivalent. Now it turns out when you go to university, you're going to learn some more details around this, but they're not part of our course, and so we will assume that they are 50-50 and equally likely. Checking out a different isomer, this is now but-2-ene, and when we add a small molecule to but-2-ene, in this case we're going to add steam, then we produce this molecule. Because of the position of the double bond, if we add the OH on this 2 carbon, then we produce the product as shown here. But if we add the OH on the 3 carbon, then we produce the same product here, because there's effectively no 3 carbon, because we have 2 equivalent positions, and if we just flip the molecule around, or look at it from the other side, then they are equal. And so there's no way to differentiate them, and effectively we don't have a 3 carbon position to add to. So we can add in either of these positions and produce this one product, which means that we only have space for one product in this particular reaction. Not because it's not possible to form two, but because in this particular reaction, the two products that get formed are chemically identical. I'll give you a chance to name this product. This is butanol. We can produce alcohols from alkenes as we've just looked at. We can also produce alcohols from alkyl halides. Here's an example. We take this alkyl chloride, to it we add sodium hydroxide, and our products are this alcohol and sodium chloride. I'll give you a chance to name the organic molecules. Our reactant is 2-chlorobutane and our product is butanol. So as you can see, this presentation has shown that there are two ways to synthesize alcohols. Firstly, we can do it from an alkene. I'll give you a chance to name this one. This is methylpropene. We don't need to number where the double bond is, and nor do we need to number where the methyl group goes, because there are no other possible arrangements of this molecule that are structurally different from methylpropene. If we react that with steam, then we produce this alcohol, which I'll give you a chance to name. This is 2-methylpropanol. This is a tertiary alcohol. This molecule is commonly known as T-butanol. Its proper name is 2-methylpropanol, and because there's only one way to arrange a tertiary molecule with 4 carbons, we can call this one tertiary butanol. If we happen to react methylpropene, our reactant here, with hydrogen bromide, we will produce this product. I'll give you a chance to name it. This is 2-bromo-2-methylpropane. We can react 2-bromo-2-methylpropane with sodium hydroxide and produce 2-methylpropanol, our final product. And so we've outlined here two possible ways that we might synthesize this desired alcohol. In the lab, a chemist might choose one of these two reactants based on the cost or perhaps its availability. The information sheet that you'll be provided in the end of year exam contains a flowchart We're going to investigate that flowchart and we're going to build up to it with our explanations throughout this video series. Today, we've started with an alkene, to which we can add hydrogen gas to produce an alkane. If we take that same alkene and add a hydrogen halide, we produce an alkyl halide. And finally, if we add steam to our alkene, we produce an alcohol. We can also produce an alkyl halide from an alkane by adding a halogen. I've grayed this out because this isn't discussed directly in this course, although it is discussed in physical sciences, so this is assumed knowledge. This reaction path is not shown on your information sheet, but you should be aware of it. Finally, we have the option to add sodium hydroxide to our alkyl halide to produce our desired alcohol. That's it for today's lesson on the synthesis of alcohols. Our next video is going to look at what we can synthesize using those alcohols. I hope this all made sense, and I'll see you guys next time.